Let's take a look at this question. Question number 5. A demolition ball is used by a crane to break the wall of a building. The demolition ball of mass 1,250 kilograms is lifted by the crane to a point R at a height of 5.8 meters above its lowest position in 60 seconds. Ignore air friction. Okay, important. 5.2, calculate the average power dissipated by the crane in lifting the demolition ball to point R. So the formula to calculate average power, question 5.2, average power is equal to force multiplied by V average. What force are we going to use? So in this question, we should think about, let's look at a free body diagram quickly. The crane is pulling the object up using tension, and there's a force of gravity, right? So the crane is pulling up against the force of gravity. So that force that it's pulling up with is going to equal the force of gravity. So it's going to be mg and V average. The mass is 1,250. Gravity is 9,8. And now for the velocity, well, we know the distance that it was lifted. We know the time that it took to lift. So we can work out the average velocity using distance over time. 5,8 divided by 60. And that's equal to 1,184,17 watts. Okay. Next question. The demolition ball is released from point R and strikes the wall at the lowest point of its swing. The ball then moves 0.25 meters horizontally into the wall before coming to rest. 5.4. Is the force which the wall exerts on the ball a conservative or non-conservative force? This is a non-conservative force. Remember our conservative forces, we have a list of conservative forces, gravity being one of them. It's important that you learn these forces, okay? Remember, a conservative force is independent of the path taken. Question 5.5. State the energy conversion that takes place during the downward swing of the demolition ball. So the demolition ball is held at point R and it's held stationary at point R. That's what they told us. So there's no kinetic energy there. So it's being held at point R at some height. So it's going to have gravitational potential energy, EP. And then as it swings, it's moving, and so that EP is then going to be converted to EK. So the energy conversion is going to be gravitational potential energy that's going to be converted to kinetic energy. Last question, question 5.6. Using energy principles, calculate the magnitude of the average force exerted on the ball while it moves into the wall. Now for 5 marks, again, simultaneous or multiple equations. So what I've done here is I've drawn a sketch of basically what happens. So this object, the wrecking ball is being held at rest. It then swings and then collides with the building. And then when it collides with the building, it travels horizontally 0.25 meters and it stops. Okay, now we are interested in this portion because remember the wall is going to exert a force on the ball when it's moving inside this building, right? Now here we can use W net is equal to delta EK, right? But what's missing is that we don't know the velocity at which this crane hits the building, right? Remember, at this point at the top, it's held at rest, it swings, and then it hits the building here. We don't know that velocity, but we can work out that velocity. And we can use grade 10 energy principles. So remember, there is no air friction, right? So what we can do is we can say that the velocity at which it hits the building is going to equal the square root of 2gh. Now, the way that this formula is derived, it may not be applicable, you may not be able to use it, though it is a useful equation. I'll show you how we get it in a moment. So 2, then 9,8, and then the height is 5,8. That means that this crane hits the building at a velocity of 10,66 meters per second. That's going to be our initial velocity here. So our VI is 10,66, and then it stops, which means my VF is 0. I got the delta X. I can work out the force. So when this object, when this crane, when this ball is traveling in the building, there is a force that's slowing it down that way. This is the force of the wall on the block, or on the ball, the wall on the ball. Okay, that's the force that they want, right? And that's really the only force that's acting on it. So W net is going to equal the work done by this force, and that's going to equal half mv squared final minus half mv squared initial. Now this force is the force times delta x times cos theta. That's equal to half mv squared final minus half mv squared initial. Now we can substitute. We don't know the force, but we want the force, right? This is the force of the wall again, right? This is the force of the wall. Delta x is 0,25. The ball is traveling to the right, but the force is to the left. So it's cos 180. That's equal to half 1250. VF is 0 squared minus half 1250. VI we worked out as 10,66 squared. The only thing we don't know now is the force. We can solve it. The force of the wall on the ball is therefore going to equal 284,089 newtons. And that's it. Now, let me just take a second to show you how we can get this formula, because it is important. You may not necessarily get marks for doing it like this, though it is a quicker method. Now, the way that that formula is derived is you will say that the mechanical energy at one point, let's say same thing here, there's the wrecking ball, and the wrecking ball moves down to this point here. So from here, let's call that point A, let's call that point B. So the mechanical energy at A is equal to the mechanical energy at B. Now it's being held at rest here, right? And this is the bottom. Okay? So mechanical energy is equal to mgh plus half mv squared, and that's equal to half mv squared plus mgh. Now, since the object at B is on the ground or at the bottom, we say mgh is 0. Since the object is held at rest at the top, half mv squared is 0. So we're going to be left with mgh equals half mv squared. Now we can cancel the masses, and we can take this half over and solve for v. You get v equals the square root of 2gh. And that's how you get the formula. Now, of course, if you did it like this, it's a longer way, but you would also definitely get the marks instead of using the shortcut. But you can use the shortcut just to verify. Okay? If you like this video, leave a like, share, subscribe. If there's something specific you'd like me to do, let me know in the comment section below. Until the next one, bye-bye.